Right. So tensile, compressive and bending belong to the category of normal, and shear and torsion belong to the category of shear. Okay. So now if you have a round bar and you are holding it in your hand and you are twisting it from the opposite, twisting it, trying to rotate it in one direction from the top and rotate it in the opposite direction from the other side. This is called torsion, torsional load, right? Torsional load. Like when you are trying to put a screw inside a piece, a screw, right, with a screwdriver, then you are applying torsion, twist, 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 torsion, right? So this torsional load also applies shear, and if you know normal shear, you have a flat plate and you are trying to cut it with a knife or cut it with a blade, then you are shearing it. So whether it is a direct shear force or it is a torsional force, it is called shear. Okay. So that is what we are saying. Another important type of loading as compared to tensile is shear loading. Material is under a shear stress. The symbol is now tau, right? Again in Latin, Greek, this is like T, but this is tau, T-A-U, tau. It has the sound of T. So shear stress is there if a shear force couple is applied to two opposite parallel forces of the cube. We will show you just now that if there is a shear force, we will show you the figure. But just remember that normal force means if there is an area, the force is at 90 degrees to the area. If the force is parallel to the area, then it is a shear force that you know. So that is what we will show you in the figure. But definition of stress is the same. Definition is force upon area. So now it is shear stress. So it is shear force upon average area. So the area on which it acts and the force, which is the shear force this time. The unit is still the same, PSI or Pascal, right? So this is because we know already stress now. It is just that compared to normal load, which was at 90 degrees, now the load is a shear load, which is tangential or parallel to the surface. So this is shear stress. And a strain is again the same thing. A strain earlier was what? Change in length upon original length. So now shear strain, amount of shear displacement, change in length because of shear upon the original distance, right? So amount of shear displacement upon displacement over which shear acts. So this is change in length due to shear and original length. Its symbol is gamma. The symbol gamma is for shear strain, and you will see in the figure, we will just show you that the change in length is A and the original length is H. And we will see later on that the way this is now, this is also equal to tan of theta. We will show you there, right? So shear stress is tau, shear strain is gamma. If you remember, I don't know if we discussed it, that when we are applying normal load and we are talking of a stress and a strain, then if the deformation is elastic, when you remove the load, all the deformation goes away. So how is elastic deformation defined technically? For all metals and so on, it is a straight line, right? For all metals and alloys, it is a straight line. A straight line means that both the quantities, it is a stress on one side, a strain on one side, and it is a straight line. So both the quantities are directly proportional. So sigma stress is directly proportional to epsilon strain, and the slope of the line we will see is the elastic modulus E. So sigma is equal to E epsilon will be the equation. So similarly here, if it is shear stress and if it is shear strain, tau and gamma, then tau is equal to G gamma. It was sigma is equal to E epsilon. E was the Young's modulus or the elastic modulus. So here G is known as the shear modulus. And rather than pure shear loads, if we apply torsional loading also, then it can be achieved. So in the actual machine where we do this test, it is very difficult to take a plate and try to cut it with a blade. But it is much easier to take a round piece and apply torsion on it, apply twist on it, torsion. So yes, in the real machine, the test is done by using a torsional load rather than a simple shear load. So now let us see the same quantities on. Before we go to the figure, we are showing you different standard materials like aluminum alloys and coppers and steels and titanium and tungsten, and three major quantities now. Modulus of elasticity, this is capital E. Shear modulus, it is capital G, and Poisson's ratio, it is nu. So you see, already we have discussed, this means three material properties. You see, we told you that we are discussing stress and strain, because based on stress and strain, we can understand material properties. So we will study these material properties in more detail later on, but just by already knowing that for normal loads, tensile or compressive, the equation is sigma is equal to capital E epsilon. Sigma is a stress, epsilon is a strain, and capital E is Young's modulus or modulus of elasticity. So this value is already there. In case of torsional or shear load, tau is equal to capital G gamma. Tau is shear stress, gamma is shear strain, and capital G is the shear modulus. We will see later on that in some books, shear modulus capital G is also called modulus of rigidity. Modulus of rigidity, how rigid the material is. And Poisson's ratio nu we have already discussed. So all these three are material properties. Material properties. They have one value for one material. Okay. So now we are just showing you, right? Just showing you the same thing as we had earlier, that suppose this is a piece of material. If we apply a load at an angle to the surface, you know by your very basic vector mechanics that you can divide it into a component which is tangential, which is perpendicular to the surface, and a component which is normal, right? Normal, and another which is tangential or parallel. So this normal is the tensile one, this parallel is the shear. So any force, if it is not at a particular angle, if it is at any general angle, then this force can be divided into a tensile component and into a shear component. Tensile component we done earlier, shear component is what we were talking about just now, right? So this is it. Now this shear force upon the area of this surface, is called shear stress. And again, the A naught means the area before deformation. After deformation, if this area changes, that is something else. But just like normal stress, engineering stress, here it is shear force upon the shear area. And here we are summarizing it. That you see the tensile part, right? This black portion was there. Under tensile load, it became green in color. So the original length was L naught. The original width was W naught, and it changed by a total size of delta. So delta by 2 there, delta by 2 there. Okay. So a strain is delta upon L naught, change in length upon original length. And if you find this delta, right, this is a strain in this direction, then multiply this strain by nu and you will get the other one. Of course, the other one, if we can find the change in W naught, right? The change in W naught. So that will be the other one. Now, in case of shear strain, this was the original. The black one was the original. We applied a shear force on this upper side in this direction. So what happened? After some time, this is fixed. The bottom, suppose, is fixed. Then the top portion moved because of this sliding force, and the piece became this red one. So this delta x is the change in length, and it is changed in respect to this length. So delta x upon y is the shear strain, delta x upon y. In the other diagram, it was A and H. You will see in the notes, this was a small a, this change in length was a small a, and this height was h. So we were calling it a upon h. Here we are calling it delta x upon y. It is the same thing, right? But now, because it is length on this side and length on this side, isn't it? So if there is an angle, if the total angle is 90, right? This is 90 minus theta, so it means this angle is theta. So if I take tan theta, if this is theta, tan theta, you see this is theta. So tan theta is delta x upon y. You understand, right? Tan theta is delta x upon y. Tan theta is delta x upon y. So therefore, the strain which was defined as delta x upon y can also be called tan theta. So whether we measure the change in length and the original length, or we measure the angle that has happened because of this shear force, it is equal to tan theta. So tensile strain, change in length upon original length; shear strain, change in length on the shear direction upon the other length which has moved, or equal to tan theta, right? So this is types of strain, tensile strain, shear strain, and these are both engineering strains, meaning that we will divide by original length and so on. Okay? Here we are telling you in general that you see, if you go to any park where there are rides and so on, then there is tensile load, there is compressive load, there is torsional load. So all types of loads are there, right? Simple tension is this thing. Torsion is this thing, right? That there is something, we are trying to twist it in that direction up above and in this direction below. This is torsion. And because of torsion, there is a shear force created. And you know that this is like this. So there can be tension, compression, simple shear, torsion. I am giving you more example, that you see here it is a bridge, and below the bridge there is this big truss structure. So in all the truss, whenever something moves up there or the weight of the bridge, there is big compressive load. Here, for example, there is this big rock and there is this bottom column, so there is a big compression. So from real world, we are just telling you that all types of actual loads, tension, compression, shear, torsion, and sometimes bending, right? All are there. Now, I don't know whether what you felt in the previous course, that, oh my goodness, this is very complicated. We have so many different types of loads. So if there is a combined loading, right? If it is only tension, okay. If it is only shear, okay. If it is a combined loading, it is a very complicated problem. So people always get afraid. You will do the same thing in solid mechanics, that, oh my goodness, complex loading. But you see, the thing is that in your Tanivia here in math, you have done vector mechanics. So if there is a force at an angle, you can divide it into components. So you solve only the tensile load, then you solve only the compressive, then you solve only the shear, and each time you find the x, y, z components of the force. Fx for tension, Fx for compression, Fx for shear, x, y, z components. In the end, you have vector addition, right? Vector addition, x, y, z forces. So you can find the combined load and you can find the combined angle. So it is just a fear in your mind that the problem is complicated. It is not complicated, it is simple, but it will take time. Just divide the forces into their components and solve for each component separately. In the end, do vector addition and you are done. So there should be no fear. Their time will be there, but it is simple, not difficult to understand.